to Sorcerer's classes. In this video today, we're going to discuss some of the concepts that are related to some of the problems that you can encounter in the IIT JAM entrance exam. And what I'll be doing in this video is to basically clear up some of the concepts that are related to the topics that you have already studied in the class, but you probably have forgotten or missed, and which you will need or might come in handy during the exam. Because what I've said even before, in most of the cases, you don't actually need to solve the problem by actually sitting down to solve it. You don't have to solve anything, to be honest. You can just utilize the concept underlying the problem and just get away with it. You can just guess, you can just make an educated guess, or you can just eliminate out all the wrong options. And that's all that matters in the entrance exam. So today we're actually going to cover a topic in electrostatics. So we've already done one topic previously, which covered Coulomb's law and the basics related to Coulomb's law and the electric potential and equipotential surfaces, electric field lines, and how we can find the how we can solve for one by knowing the differential equation of the other, using the concept of orthogonal trajectories. And today we are actually going to go over to another related concept known as Gauss's law. The Gauss's law for electrostatics. And what is Gauss's law? You already know this, so I'll not be going into detail of actual statement of Gauss's law. I'll just draw the diagram. So let's say this is a closed surface. What do you mean by a closed surface? The closed surface is a surface which encloses a volume. So let's say I show you this. So this surface is not a closed surface. This is not enclosing any volume. Whereas if I show you this marker pen, and if I ask you, is the cylinder a closed surface? The answer is yes. It is a closed surface because it is enclosing a volume, namely the volume of the cylinder. It's enclosing a volume, so it's a closed surface. And actually, if you consider the cardboard, I have actually neglected the thickness of the cardboard, because otherwise the whole cardboard is also a closed surface. But if you neglect it, if you just consider the plain surface, then this is not a closed surface. This is actually an open surface. And Gauss's law concerns two things. It concerns the volume enclosed by the closed surface and the surface enclosing it. The surface enclosing it. Let's just say the surface enclosing the volume is S. So in electrostatics, Gauss's law simply states that E dot ds, which is the closed surface integral of E over S, is simply proportional to the total amount of charge enclosed by that surface. So depending on how much charge your closed surface has enclosed, the surface integral of the electric field basically should tell you the amount of charge that is enclosed inside the surface. I said that it has something to do with volume enclosed. So for that, of course, you need something called the Gauss's divergence theorem. The Gauss's divergence theorem simply says that if you have a volume integral of the divergence of E in a volume enclosed, in a divergence of E through a volume V, that is equal to closed surface integral. This circle implies closed surface integral of E, closed surface integral over the surface enclosing the volume. So essentially this is equal to this, and this says that the closed surface integral equals the total amount of charge enclosed by the surface. And this is an extremely useful equation in electrostatics. When you're trying to solve electrostatic problems, often you can actually get away by using Gauss's law instead of having to work with Coulomb's law and solving electric field. And actually, charges may not be even discrete charges. It can be a continuous charge distribution. It can be a continuous charge distribution, for which case you need to consider a volume charge distribution characterized by a volume charge density. A volume charge density. And in that case, the Gauss's law simply tells you that E dot ds is 1 over epsilon times the volume integral of rho times dV. What if you have a surface charge distribution within it? Let's say it's a sigma. It's also very straightforward. It's sigma ds. And if you have a line charge distribution, it's just simply lambda times dl. So the lambda and sigma are the expressions for surface charge, for surface density, and lambda is for line density. Line density of charges. That's it. This does not have any other significance. They're just chosen for historical reasons. And this surface is often called a Gaussian surface. A Gaussian surface. So now the Gaussian surface, now there is one aspect of Gauss's law that we don't recognize a lot of times, is that the Gaussian surface or what we can say Gauss's law is true in general. Whether it is possible to draw the Gaussian surface or not, that does not matter. It may not be possible to draw the Gaussian surface if you don't have symmetry, if you don't have radial symmetry, if you don't have spherical, if you don't have symmetry, it's not possible to draw the Gaussian surface in general. To draw the Gaussian surface, you actually need a symmetric problem. For instance, if you have a single charge cube, you can see that the electric field lines are all radial. The electric field lines are all radial, and the electric field is 1 by r squared. And what is the Gaussian surface here? The Gaussian surface, you can see from the symmetry of the problem, the Gaussian surface has to be a sphere. The Gaussian surface has to be a sphere, and you can actually use it. You can use the Gaussian surface formula to actually calculate the electric field, and you see that if you have to calculate the electric field on the Gaussian surface, you know that at the sphere, at every point on the sphere, the electric field is constant because it's at a constant distance from Q. And so you can take the electric field out of the integral, the ds stays inside, and E and ds are actually parallel. So you can basically make this a scalar product, and ds is actually 4 pi r squared dr q over epsilon naught. Q over epsilon naught. And so, r squared dr, but r is fixed on the sphere. ds, the r is fixed. R is already fixed. R squared dr. 4 pi r squared ds. Actually, it's not 4 pi r squared dr. The ds is whether the ds is 4 pi r squared. It's not 4 pi r squared dr would be a volume. And ds, the surface integral, is 4 pi r squared, and it's q over epsilon naught, and E comes out to be 1 over 4 pi epsilon naught q squared. Just the thing we obtained. just the usual Coulomb's law. However, let's say a very simple example. Let's say we have a dipole. We have a dipole, and we are asked to draw the Gaussian surface for it. It's not possible. You actually cannot draw the Gaussian surface so trivially here, because the dipolar fields are not spherically symmetric fields. You see that the dipolar fields look like this. They come out from the positive charge, end at the negative charge. The dipolar fields are not spherically symmetric, and you cannot draw the Gaussian surface for it. In fact, if you try to draw any spherical surface around it, it will give you the total flux to be zero. It will give you total flux to be zero, and you cannot solve that for the electric field at all. So the Gaussian surface can be easily drawn only for symmetric cases. Only for symmetric cases. Radially symmetric. You can just say radially symmetric cases. At best, radially symmetric cases. Otherwise, you cannot draw the Gaussian surface. And it will still hold, but you cannot draw it. And there is another form of Gauss's law. So this was the integral form. Alright, this was the integral form, which is q over epsilon naught. But you can take this to volume integral, like I said, according to divergence theorem, dv. And this can be written as, if it's a continuous charge distribution, it can be written as rho dv. And you see, if dv is arbitrary, the gradient of E is rho over epsilon naught, and this is differential form of Gauss's law. You see, when you're given in this case, when you're given an electric field, you can calculate rho. You can actually calculate the charge density when electric field is given. Whereas in the other case, you have the charge and you have to calculate electric field. Here, the electric field is given and you can calculate rho backwards if you use the differential form of Gauss's law. And so these are the two forms of Gauss's law which has to be kept in mind when you are actually trying to solve a problem, an electrostatic problem. And oftentimes you actually don't work with Coulomb's law at all. It's much better to actually refer to Gauss's law. And you see that in Gauss's law you can either work out the electric field when the charge density is known, or you can work out the electric field when the total charge is known. By the way, is it possible to write down discrete charges as charge distribution? Of course it is. It is possible. Let's see if you have a charge Q. How can you write it down as a density distribution? And the answer comes through the delta function, or rather three-dimensional delta function. So delta function basically is a very weird kind of function. It is 0 when r is not equal to 0, and it's infinity when r is equal to 0. It looks very bizarre, but the delta function's main property is that d3 of r you know is equal to 1. This is the property, and this is what is used. So if you have to write down the rho, the volume charge distribution for a discrete charge, you can simply write it as q times delta cube r, q times delta cube r, because you see what happens. The charge distribution blows up at r equals to 0, where the charge is located. The charge distribution, the charge density is infinite there, because it's a point charge. It's a point charge, so charge distribution is infinite. But everywhere else it's 0, but when you actually perform the volume integration, which is rho dV, you actually get Q. So this works. So this discrete charge can be always written in terms of it has a distribution with the help of the delta function. So I hope you found this useful, and thanks for watching. Have a good day.